Hello, in this video we're going to continue with our discussion on inductance and the use of coils and then a circuit that is supplied with alternating current. Now, remember when we were talking about coils, we talked about something that's called induction. Induction is the resistance to the change of current in the circuit. So basically what's going on is if I take a current and I pass it through a coil, because remember, anytime you have a current that's flowing through a wire, you also have a magnetic field that expands out from the conductor and then eventually stabilizes and circles around or flows around the conductor. Well, in a coil, because you have the coil wrapped up, remember that the other rule is that whenever magnetic lines of force pass through a conductor or cut across a conductor, it generates a voltage, and that voltage is opposite in polarity to the applied or source voltage. So what this means is that voltage, it's a sort of like a counter pressure that opposes the flow of current. And it's very similar to resistance, but it all depends on several different things. For one thing, the higher the frequency, the more that magnetic field is expanding outward and collapsing. Thus, the more it's cutting across the conductor, and thus the more opposition you have to current flow. And so we talked in the last video about the formula for finding inductive reactance, which is similar to resistance, and we talked about it being 2 times pi times the frequency times the inductance value, which is measured in henries. And remember that as the frequency goes up, then so does your resistive or reactive value. So as the frequency goes up, the coil limits the flow of current more, so your current goes down because you have more opposition to the current flow. So let's take an example just to show you what I'm talking about. Here we have a circuit that's hooked up to a 480 volt power source that is operating at 60 hertz or 60 cycles per second, which is what the standard voltages are here in the United States. And we have, the only thing that we have that's limiting or opposing the current in this circuit is a coil. And all we know about this coil is that it has an inductance value of 0.5 henries. Let me get a drink, my throat's dry. And so this 0.5 henries we can use to figure out how much resistance or opposition to the current flow we have in this circuit. So we take our formula, 2 times pi. We know that the frequency is 60 cycles a second or 60 hertz. So we multiply that by 2 pi and then by the inductance value of 0.5. And this gives us an overall reactance value of 188.5. Okay, so now that we know that, we can know how much current's flowing through our circuit, because here this inductive reactance, because it's the only thing that's in the circuit, we can just use it in place of resistance in our formula, E equals I times R. In this case, we're going to use Z because Z represents impedance, which could be inductive reactance or it could be resistance or whatever. So we plug it in. We have 480 volts, and then our current limiting factor here is the inductive reactance, which is 188.5 ohms, because inductive reactance, like resistance, is measured in ohms. We divide that out and we get a current flow of 2.55 amps. We could also find the power that's used in this circuit, although I say used. Actually, if you have a circuit that is purely inductive, that is, it only has coils but no resistors, it's not really using any power. What it's doing is it's pulling that energy out and storing it in the form of a magnetic field, and then when the magnetic field collapses, it puts the power back into the circuit. So this is actually what's referred to as apparent power, although apparent power in a purely inductive circuit is found in the same manner that you would find power in any other, in a purely resistive circuit, I should say. And so all we do is multiply our voltage by the current. So I can take 480 volts times 2.55 amps, and I have an apparent power of 1,222.3 volt amps as opposed to watts. Use volt amps just to show that this is apparent power, and that unlike a resistive circuit, the power is not used or expended as it would be if this were a resistor, where it would be dissipated or essentially wasted as heat. Here we're actually just storing our power in the form of a magnetic field and then returning it back to the circuit. Now, what if I have a circuit that has both a resistor and a coil? Can we just add these two values together to get our total impedance or opposition to current flow? Unfortunately, we can't, because the resistor is in phase with the source here, so everything's operating basically in phase. But because when you put a coil in a circuit, that causes the as far as this coil is concerned, the current is lagging the voltage by 90 degrees. So what that means is that our coil and our resistor are 90 degrees out of phase. So the only way we can add these two together is using, we have to take vectors into account. We have to take into account that this resistance is occurring in one direction that is 90 degrees off, or that leads the opposition to current flow by 90 degrees that's exerted by our coil. So let's see how this works. I'm given the resistance in this circuit. I know that the resistor has a resistance of 12 ohms, but the only thing I know about my coil is that it has an inductance value of 0.053 henries. Well, if you think back to our formula, all we have to do is know the frequency, which we do. It says it's 60 hertz, and we multiply that by 2 times pi times the frequency, 60 hertz, times our inductor value of 0.053 henries, and we find out that in this particular circuit, and given this particular frequency, our coil is offering 19.98 ohms of opposition to the current flow, or reactance. Okay, now that we have those two values, we can figure out what our total impedance is in the circuit, and then figure out what the current flow is. So what we're going to have to do, because these are 90 degrees out of phase, we're going to treat this as a right triangle. So we're going to plot our resistance value on this horizontal axis, and then we're going to plot our inductive reactance value on this vertical axis here. And notice that if I sort of dot in some lines to represent a line parallel to the resistance, and then another line which is parallel to my inductive reactance, I form a box. And if we want to draw a line right through the middle of this box here, it forms essentially two right triangles. Well, this line that forms the hypotenuse of both of these right triangles is going to be our total impedance value. In other words, that's the value that we come up with when we add vectorially our resistance and our inductive reactance, which are 90 degrees out of phase. So one thing we can do, since this is a right triangle, is we can use Pythagorean's theorem, and we can take our R value, in other words this 12 ohms squared, plus the inductive reactance value squared, which is this 19.98 ohms, and that's going to give us our total impedance. We're going to rearrange the formula. We're going to go ahead and take the square root so that we have the z term reduced, the impedance reduced to its just its base value here, and that means we're going to end up taking the square root of the sum of the inductive reactance squared plus the resistance squared. So I just plug those numbers in, and I have for my inductive reactance 19.98 squared plus 12 squared, and then I add this together, take the square root, and I get a total impedance or opposition to current flow of 23.3 ohms. Now that I have this value, I can go back over and just use my Ohm's law formula, which is usually it would be E equals I times R. But since we have both resistance and reactance in this circuit, we're going to replace the R with the letter Z, which in electronics stands for impedance. So I have this formula E, in other words, the voltage is equal to the I, or the current in amps, times the Z value, which is the total impedance. I rearrange the formula to solve for the current, and so now I wind up with E over Z equals the current flow. And then I just plug in the numbers, 480 volts divided by 23.3 ohms, and that's going to give me a total current in this circuit of 20.59 amps. Okay, I can check myself by using trigonometry. If you want to go that route, you can take the tangent just to double check your value. So since this forms a right triangle here, and remember that in trigonometry you have these different ratios of one side to the length of another side, well, we can take the tangent, since we know the opposite, this opposite side, we know its length, and we know the adjacent side to this angle right here, which is called angle theta, or the phase angle. We can take that and then use that later in our sine formula to check ourselves. So in my calculator, I hit the inverse function, tangent, and then I plug in my numbers. The opposite side here, which was 19.98 over 12, because that's the resistance, and that gives me an angle, this angle right here, it has to be 59 degrees given the ratio of those two sides. Once I know that, I can switch to a different function, which is called the sine function, and I just plug this in and use a little algebra to double check my numbers. So I have sine of the angle 59, or my phase angle, is the opposite over the hypotenuse. Well, in this case, the hypotenuse is the unknown value. It's the Z value. So I'm going to put in sine of angle 59 equals 19.98, that's the opposite side here, over my hypotenuse, the unknown. I'm going to isolate that h there so I can solve for h. So the first thing that I do is, let's see, what did I do here? I'm looking at it backwards. Okay, I multiply both sides by h so that I could get the h in the numerator. And then once I do that, I have the equation as the sine of angle 59, phase angle, which is at 59 degrees, times h equals 19.98. Now I'm going to divide both sides by the sine of this phase angle of 59 degrees. So I wind up with h equals 19.98 divided by the sine of angle theta, which is 59 degrees, and that's going to give me the value of 23.3, which matches with my other equation where I used Pythagorean theorem, and also got a result of 23.3. Now that we know the current flow in the circuit, we can also find out how much power is used. And remember, there's going to be two values here. There's an apparent power, which is going to be the total when I multiply the voltage by the current. But that's not really true power, because remember, the power that is as far as the coil is concerned is not used. It's stored in the form of a magnetic field. Now the power that is generated by the resistor is dissipated in the form of heat, so that would be true power, which would be it could be measured in watts. So to get my apparent power, the first thing I need to do is just plug in my formula, which is P equals the E times I, where E stands for the total voltage in the circuit and I stands for the total current. So we know that the circuit operated at 480 volts. We found the current to be, 20.59 amps, and we come up with an apparent power of 9,885.586 volt amps. But remember, as part of this power is stored, it's not actually used. Only the power that runs through the resistor is dissipated or wasted as heat. To find that, we're going to have to find a ratio here, which is referred to as the power factor. There are several different ways to find the power factor for a circuit, but one easy way is just to divide your resistance by the total impedance. Well, our total opposition to current flow was this 23.3 ohms. Our resistor value was of 12 ohms. Or had a value of 12 ohms. So when we divide 12 ohms by 23.3, we get 0.51, and expressed as a percent, this would be our power factor of 51%. So what that means is that only 51% of the power is true power, basically. The rest of it's stored because it's being generated by the coil. So now to find the actual true power that is dissipated, as I said, in the form of heat, we just plug in our apparent power, which was the voltage times the current. It gave us a value of 9,885.586 volt amps times this power factor of 0.51. And this circuit is dissipating 5,091.28 watts of true power through our resistor. So that's how you can figure out the different values when you have what's called an LR circuit. In other words, a circuit that has both inductors or coils and resistors. So we'll kind of expand on this later. We'll talk about transformers. Transformers are really cool because they're very energy efficient devices, and it's because we can use transformers with AC. That's one of the reasons why we use AC instead of running everything on DC, because it's really easy to step up the voltage or step down the voltage using transformers at the end user side. So we'll talk about that in another video, and then we'll also talk about capacitors, how they are similar to inductors or coils and how they differ, and then how you would solve for the different values if you have a circuit that's got capacitance or capacitive reactance versus inductive reactance. And then we'll talk about how you can solve where you have a circuit that has a coil, a capacitor, and resistors. Thanks.